The whole mechanism of this reaction is going to be a bit like. Hello everyone. So today we are going to discuss about the next reaction of this alkyl halide preparation. We were discussing regarding how we can prepare these alkyl halide from alkene. So in the previous lecture we have discussed how we can prepare from this through a electrophilic addition reaction. We have discussed in the previous lecture, in which we have discussed a bit regarding detail about the Markovnikov rule, why we are adding, how we are adding this HX part on this alkene part. And today we are going to discuss a new concept, that is addition of this alkene with HX in the free radical mechanism. How this reaction is proceeding. So first, if we are having this alkene, this is our alkene, and we are reacting with it HX in presence of peroxide. In presence of a peroxide, so what is going to happen over here? We will see this bond will break, homolytic cleavage will be there, and this we are going to get a product like this. Sorry. One side hydrogen and another side halogen. But how the same question arises, what will be this management of this X and H, where we are going to add this H, where we are going to add this X, and is there any possibilities that all these HX will be doing a similar type of reaction in the presence of peroxide, or they are going to behave differently in the presence of this peroxide? That we are going to discuss in this today's lecture. So the first thing is that this is going to be in the presence of a peroxide. This type of mechanism which I am going to discuss will be in the presence of peroxide. The whole mechanism of this reaction, is going to be a bit like we are using a peroxide. So which means there is going to be a peroxide bond, which means oxygen-oxygen bond. And we know it is a very, very weak bond, and it will break down like this. This RO bond is going to break down like this. And what will happen? You know, we are already having this HX. And in this reaction, the main HX which we are going to use is only HBr, which is going to play a major role, not all other HCl, HI and HF. And I will discuss that point also, why all other HI, HCl and HF are not taking a role in this type of peroxide effect. So yeah, so we are taking HBr in this. I will tell you why only HBr. So this RO is going to react with HBr, and you know this bond is going to break over here. This bond is going to break over here, and we will get alcohol. We are going to alcohol and a Br free radical, and a Br free radical. What we are going to get? A Br free radical. Now this Br free radical, it is highly reactive. What it will do? It will react with our alkene. If this type of alkene we are using unsymmetrical, in this I have shown you the symmetrical, where there was no effect, that where we are adding this hydrogen or halogen. But in this, the question arises where we have to add this Br free radical. So now we will be having two possibilities. Two possibilities arise. One is that this add up over here. The another will be it can add at this side. So we will observe this CH2 single bond. Sorry, yeah, I made a mistake. it will attack at double bond because it is quite reactive. Just by mistake I drawn this, yeah. So it will be like CH2 single bond CH single bond CH3. Now if you are adding firstly at this side, so this will be like Br like this, and over here a free radical generation. And another possibility will be like this. If you are, this is the second step, so we can see CH2 single bond CH single bond CH3. So now we can visualize over here a free radical, and at the center we are adding a Br. So Br, two possibility of attaching of Br. So now you can see this is more stable, because as same as the free radical, 3 degree more stable than 2 degree and 1 degree. This is the stability of free radical. So we can see the reaction is going to proceed through this pathway. More stable free radical. This is the more stable free radical. So this is our most important first step. Over here we are getting this, and after that what will happen? So if I draw this hole in the next step, that would be a better way. CH2 double bond CH single bond CH3 plus HBr, sorry, plus Br free radical will give us CH2Br, this one, yes or no? Over here a free radical, CH free radical and CH3. So now what will happen? This HBr, which is already present with us, it will again break down. It will break down like this homolytic, and this hydrogen likes carbon more. It will like the more the carbon, and it will break down from this HBr, and it will move to this carbon, and we are going to get CH3, sorry, CH2Br single bond CH, over here hydrogen, and CH3 like this. This is the whole mechanism how this reaction is going to proceed. You can see over here, visualize this Br and this H. And if you visualize over here regarding the Markovnikov rule, in the Markovnikov rule, I have told you that adenum will, negative part of adenum is going to add on the hydrogen double bonded carbon, that carbon which is having less number of hydrogen. But over here we can see it is adding to the carbon which is having more number of hydrogen. More number of hydrogen. So what is the thing which we are going to see over here? So we can see that this is the opposite of Markovnikov. So we call this thing as anti-Markovnikov. Anti-Markovnikov. Anti-Markovnikov addition. It is an anti-Markovnikov addition, or we can also say, because we are using a peroxide to initiate this reaction, so we can say peroxide effect. Another is a Kharash effect. So these are the three names for such type of arrangement. So I have shown you the mechanism also, how we are proceeding through this. It is proceeding through a free radical mechanism, and that's why we are getting the product that is opposite of Markovnikov rule of electrophilic addition. In electrophilic addition, we were getting the product where bromine or halogen or negative part of atom was adding to that carbon of double bond which was having lesser number of hydrogen. So now the very important concept I am going to tell you, HBr. Only in presence of HBr we are going to see this type of effect. So why only this type of effect? So okay. Cl, oh sorry, HF, HCl, HBr and HI. There are 4 groups are there. HX can be subdivided into 4 moieties, either HF, either HCl, either HBr or either HI. So if you come over here, in the first step what we are getting over here, this Br free radical. In the first step we are visualizing that this Br free radical is adding at this carbon is CH2 alkene. This Br free radical is very highly reactive. This Br free radical is highly reactive. So what we are going to see over here, this Br in the first step, and it is a second step. For first step, this is a free radical attaching to this alkene. So if this part you see, a more reactive group is attaching and getting some stability, so what do you think? The reaction is spontaneous, some energy is going to be released. So that type of reaction are exothermic. So free radical of F, it will be highly reactive, so it is like some exothermic. For Cl free radical, that is also just near to this fluorine, that is also a exothermic reaction. That is also a exothermic reaction. And regarding this bromine, compared to that, it is relatively less exothermic, but it is also an exothermic reaction. But when you come to this I negative, that is very stable. Here is the reactivity order and this will be the stability order. I dot R free radical are very stable. So what they are not that much reactive, they do like this, I2. They don't want to react that much to some other moieties. So that's why such type of reaction are endothermic. If we want to proceed this reaction, we have to apply some energy. We have to apply some energy. In the next step, this was we were discussing regarding the first step. Now come back to the second step. So now in the second step, if you see, in the second step we are going to see that this bond we need to break down. We need to break down this HBr bond. And what do you know? A bond breaking is a endothermic process. Bond breaking is an endothermic process. Bond breaking is an endothermic process. So we are expecting this all to be endo. Clear or not? But one more thing you need to understand over here, in the whole process, one bond is broken, another bond is forming. This bond is forming over here or not? This is breaking, but this is forming. So for that reason, we know starting two reactions are endothermic. The last two are exothermic. Because this I2 bond, I have already told you that they can be bigger molecule, larger bond, can be broken very easily. Comparative, we need less energy to provide. We need a lesser energy to break such type of bond. That's why these two are exothermic. So now if you visualize over here, exothermic, endothermic, exothermic, endothermic, exothermic, endothermic, the only reaction which is having both the process, part 1 and part 2 of our mechanism. Part 1 and part 2 of our mechanism as exothermic, that is the only case with HBr. So only we know the peroxide effect will work for only HBr. No other reaction are going to follow this peroxide effect like HCl, HI and HF. If we are adding peroxide with them, they will not follow the free radical mechanism. Instead, they will follow the electrophilic addition reaction. Either they will not take part if they take part in the reaction, some product is formed, they will not follow this, they will follow the simple rule. So now quick summary of today's lecture which we have discussed in the today's class. So in the today class, we have discussed regarding how we can prepare the alkyl halide from alkene through a free radical mechanism. In that we have seen this is the symmetric alkene when react with HX in the presence of peroxide. Two possibilities are there. One is to less number of hydrogen adenum, and another is to more number of hydrogen adenum negative part to be added. So this is the whole mechanism. I have told you how peroxide bond break down, then the alcohol formation takes place, then this free radical react with this alkene in the first step, and then the second step what happens, this again react back and we get a product with attachment of halogen, or you can say negative part of adenum at a more number of hydrogen of the alkene carbon. So this was the way, and this rule is being termed as three names I have shown you: crash effect, anti-peroxide effect, and anti-Markovnikov rule. So this is the way, and now I have already told you in the tabular form that why only HBr react with this, show this peroxide effect, not other fluorine, chlorine, bromine and iodine. So the first step of all three are exothermic, but for HI it is endothermic, because HI doesn't want to go into the I2, it reacts with itself, it doesn't like the first part of this reaction. But in the second part we have seen this, all these are bond breaking is an endothermic process, but the overall reaction we have seen over there that two of them, about two are endothermic and the last two are exothermic reactions. So that's what for this peroxide effect we have seen over here, and in the next lecture we are going to discuss a bit regarding some allylic addition of halogen at allylic carbon, and we will also see in this lecture we have seen regarding the HX bond, which means addition of HX. In the next lecture we are going to see the addition of X2. How this X2 addition is going to take place? Are they going to attach like in the same manner like we have seen in the HX, or there will be some other way how we are going to attach this X2, Cl2, Br2, I2? What is the way we are going to see over here? And also we will discuss regarding the alcohol. Also we will discuss regarding the alcohol, how this alcohol is going to add up and formation of alkyl halide takes place through this alcohol. So these things we are going to discuss in the upcoming lectures. So that's all for today. Thank you.